Hi everyone, my name is Paulo Chagas and I'm going to present our work entitled Toward Unbounded Open Site Recognition to Say I Don't Know for Glomerular Multi-lesion Classification. First of all, our work focuses on a specific kidney structure called glomerulus, mainly because kidney disease markers are mostly found in the glomerular structures, presenting varied and heterogeneous visual features. But wait, what is a glomerulus? Here we have a picture of a kidney, and with a closer look, we can see the functional unity of the kidney, called nephron. Inside the nephron, we have the so-called glomerulus, a histological structure formed by a network of capillaries. The main function of the glomeruli is the filtration of the blood that leads to urine production, as we can see the arrow of unfiltered blood entering and the arrow of filtered blood leaving the glomerulus. Due to its primary importance, lesions on glomeruli are associated with several primary and systemic kidney diseases. In our work, we use histological images usually collected via biopsy and later applying a histological stain to highlight relevant structures. Here we have an example of a fragment. Several fragments are captured with biopsy needle, and to assess individual glomeruli, the pathologist must navigate through the slide and crop each glomerulus. We can identify them by that ball-shaped structure. Here I place a cropped glomerulus so you can take a closer look. As a primary filtering structure, the glomerulus is vulnerable to many types of lesions that should be properly identified by specialists. The lesion recognition task is time-consuming and requires experienced pathologists who quite frequently do not reach a broad consensus. This way, automatic recognition of glomerular lesions emerges as a promising alternative to aid pathologists in kidney disease diagnosis. Among several artificial intelligence methods, we adopted a deep learning approach. More specifically, we use convolutional neural networks, also called CNN, which have achieved state-of-the-art results in several medical imaging tasks. But one known disadvantage of convolutional neural networks is that they usually return overconfidence scores. Why knowing when the model doesn't know? That overconfidence might be problematic when the image is not a glomerulus, or is a glomerulus with another lesion, or when the model is confident but the prediction is incorrect. So, in this work, we wanted to perform multi-lesion glomerular classification without bounding the inputs to glomerular domain or non-glomerular domain. This task is called Unbounded Open Site Recognition, where we only care about classifying the images into in or out of distribution, also called OOD. If the model defines the input as in of distribution, the multi-lesion glomerular classification can be performed. Since we cannot account for all unknown classes, a common approach is to train the model considering specific out-of-distribution classes, which can be expensive. That's why we adopted an energy-based approach to tackle this issue. We use the energy score proposed by Liu et al., where K, here we have the formula, where K is the number of classes, f of x is the output of the network, and T is a temperature scale value, which they recommended define as 1. One advantage of the method is that the energy score can be used for out-of-distribution detection without fine-tuning specific OOD data. However, they point that fine-tuning leads to better results. That's why we raise the question, how to improve the energy-based OOD detection without the costly fine-tuning process. Our hypothesis is that combining ancestor estimation methods with energy scores can tackle this issue. Now about ancestor estimation. An ancestor estimation method used was Monte Carlo dropout, but let's talk about dropout first. Here we have a standard neural network where all nodes are fully connected to every forward node. On the right, we can see the same network after applying dropout. The dropout defines a probability P to turn off any node. This method is frequently used during training as a regularization tool. Now we can define multi-color dropout. Instead of using during training, we also apply dropout during prediction. And instead of passing an input once through the network, we pass n times. One common approach is to use the average of the prediction as final label and the variance of predictions as uncertainty score. Now let's summarize the uncertainty estimation methods adopted. We already explained the multi-color dropout, and now it is clear how it adds randomness on the model. We also use test time data augmentation, which have a similar idea. We use data augmentation during prediction, introducing randomness on data. We also use ensemble of models returned from our cross-validation. I'll cover that soon. And here's a proposed pipeline for OOD detection and multi-lesion glomerular classification. The input is fed to an ensemble of models where each model performs n predictions, average the model predictions, and later the ensemble predictions. The energy score are also averaged and used to define whether an input is an OOD sample or not. We can use a threshold for that. If the energy score is greater than a given threshold T, the input is classified as OOD sample, and we can say that the model doesn't know the label. Otherwise, the input is classified as inside of distribution, and later classified as one of the training labels, which are normal, membranous nephropathy, glomerular hypercellularity, and glomerular sclerosis. As I already pointed the classes we used, now I give more details about the dataset. We use an anonymized images selected from the digital histological image library of Fiocruz, resulting in 4,682 images of human glomerulus stained with hematoxylin and eosin. Here we also have the number of images of each class, where we can note the low number of sclerosis images. We evaluated of our auto distribution method with two datasets, Caltech 101, which is an object detection dataset, and BreakHis, which is a dataset of breast cancer histology images, with the same stain of a glomerular dataset. Now let's see our evaluation protocol. Considering the glomerular dataset, we use 90% to train and leave 10% as test. The training split is used in a 5-fold cross-validation setup, generating 5 different models that will be used as ensemble. The tests and the OOD datasets are evaluated using the 5-model ensemble, and to reach a similar number of images from in and out of distribution sets, we sample 450 images from each OOD dataset, which is a number close to the glomerular test size. Here we have training details. We use the PyTorch framework. We also use wide-HasNet to pertain on ImageNet dataset for faster convergence. We trained during 100 epochs with batch size of 32. We use the initial learning rate of 0.0001 with tap decay of factor 0.1 at every 30 epochs. We use ADMW optimizer, and these are the specs of our machine. Now let's take a look on our results. I first present the results for multi-lesion glomerular classification, considering the ensemble without multicolor dropout and with multicolor dropout with p equal to 0.2 and 0.5. We can note that multicolor dropout with the p equal to 0.5 return metric is very similar to the case without multicolor dropout. Now we can see the confusion matrix. where we also compute the F1 score for each class, which showed high score for all classes. As expected, the framework performed worse for glomerular sclerosis, as it is the most underrepresented class. For OOD detection, we computed the energy score for IN and OOD, considering the proposed three wide heterogeneity variations. To compute the evaluation measures, we analyzed this energy score and defined a threshold value. These figures represent the energy histograms of IN and OOD, highlighting the fact that the OOD curves are quite close and that Caltech 101 and Break his energy distribution are very similar as well, showing a robust grouping of OOD data. As initial step towards OOD detection, we evaluated several threshold values, and I present here the results considering the best threshold value for each histogram. Here we consider the scenario of binary OOD detection, where the energy scores are used to classify only into in or out distribution. We can note that the highest area under the ROC was achieved with Monte Carlo dropout with p equal to 0.5. The results shows that a highest dropout probability allowed for a higher AUROC, which indicates a better in and OOD separation. This behavior corroborates with our initial assumption that introduce both data and model randomness from uncertainty method might lead to a better OOD separation. Here we consider the scenario of multi-class OOD detection, where the energy scores are used to classify into domain labels or out of distribution. Similar to the previous experiments, glomerular sclerosis had the worst results. Nevertheless, the weighted average F1 score, considering all classes, was 0.85, which is a promising result. As conclusion, we demonstrate that our hypothesis indeed improved AUROC for in and out recognition without fine-tuning to specific OOD datasets. The introduction of randomness from the ancestor estimation approach did not result in performance loss for both multi-lesion glomerular classification and OOD detection. Binary OOD detection showed competitive results, and multi-class OOD detection showed promising results, where more misclassification occurred in the most underrepresented class, which is a point to tackle in future work. And that's it. Thank you. Here I have some reference.